All right, last notes for this term. We're talking more about momentum. This time we are going to be talking about the conservation of momentum. Momentum is one of those quantities that is conserved. So first, before we talk about the conservation of momentum, when we talk about momentum and its conservation, we talk about it in terms of what we call a system. And a system is a defined collection of objects. For our purposes, we're going to be talking about closed, isolated systems because that is when momentum is conserved, when the system is closed and isolated. What that means, closed, obviously means that nothing can get in, nothing can get out. So no objects may enter or leave the system. And isolated means that there are no outside forces acting on the system. A lot of times we will consider our system to be like the pool balls on a pool table. That, however, is not an isolated system because the table itself, there's friction between the balls and the table, and that's what makes them slow down and stop. A puck on an air hockey table is a better example because it takes a lot longer for that thing to slow down and stop. So it's actually Newton's third law of motion that leads us to this idea that momentum is conserved within a closed, isolated system. Within a closed, isolated system, the only forces that can exist are forces that happen between the objects that are in the system. And Newton's third law says that when those objects come into contact with each other, they will experience the same force. When a force is applied by one thing onto another, the second object applies the same amount of force back on the first, right? Newton's third law. It should also be logical that they would experience that force for the exact same amount of time because they're in contact with each other. So if one experiences a force for a certain amount of time, that's how long they're in contact with each other for. So if the other one experiences the same amount of force for the same amount of time, and that gives them the same amount of impulse. If they have the same amount of impulse, then they're going to have the same change in momentum because of the impulse momentum theorem that we talked about before. So any momentum that gets lost by one object gets gained by the other one. So if you think about pool balls on a pool table, you hit that cue ball, it runs into another one. If the cue ball stops, the other one's going to have the exact same momentum that the cue ball had before it got hit by it, assuming that the ball that got hit was sitting still before the cue ball hit it. So the law of conservation of momentum, again, comes from Newton's third law. If the objects experience the same force by coming into contact with each other for the same period of time, then they're going to have the same change in momentum, the same impulse. So basically, the law of conservation of momentum says that the total momentum of a closed, isolated system does not change. It is conserved. And the way that we write that, and this equation kind of narrows it down to only two objects, and that's pretty much what we're going to stick with. So the way we'd write that mathematically is that the momentum of object A plus the momentum of object B before any type of collision takes place is the total momentum of the system. and that does not change, which means that the new momentum of object A plus the new momentum of object B adds up to the same number. So the momentum of object A plus the momentum of object B before the collision is equal to the momentum of object A plus the momentum of object B after the collision. These little marks here, that's what we call prime. P prime A and P prime B. That just shows that a new momentum. The object has a new momentum. Now, if we break that down, we know that momentum is calculated by taking the mass of the object times its velocity. So the momentum of object A before the collision is equal to the mass of object A times its velocity. Momentum of object B before the collision is equal to the mass of object B times its velocity. After the collision, the masses are going to stay the same. But the only thing that can change is their velocity. So the new momentum of object A is equal to the mass of object A times its new velocity. And the same thing for object B. The mass of object B times its new velocity would be its new momentum. And again, everything on the left side of the equals sign would add up to the same number as everything that's on the right side of the equal sign. Has to, because momentum is conserved. So this whole idea of closed isolated systems kind of brings us to the to talking about internal forces and external forces. So internal forces are forces that act between the objects that are within the system. So like when one pool ball hits another one, that's an internal force. And in that case, the momentum is conserved. If there's an external force, if it's not an isolated system, and there's an external force that takes place, like the friction between the table and the pool balls, then forces by that object from outside the system, in our case the pool table, would cause the momentum of the objects to change, and the momentum of the entire system would change. Like when you strike a cue ball and it runs into the other balls that are on the pool table, eventually all the balls come to a stop because of that external force that's created by the pool table, friction. All right, we'll come back to that in a moment. So, the equation that we showed before, there's a few different types of collisions that we talk about in terms of momentum, or events, if you want to call them that. The first one, we've already showed the conservation of momentum equation for that type of collision. That is where the objects are separate before the collision, and the equal sign kind of represents where the collision takes place. And then after the collision, the objects are still separate. They just each have a different amount of momentum now. Okay, so separate before and after. Now, there's another type of collision. This type of collision, by the way, is called an elastic collision, which means that all the force or all the energy before the collision rebounds, and we end up with the same amount of energy after the collision. Okay? So in that case, energy is also conserved. We'll talk more about that next term. There's another kind of collision called an inelastic collision. And that, as you might guess, is where the two objects are separate before the collision, and then they stick together afterward. Now, when they're stuck together, we call that, the two objects moving together, we just call that the system. So instead of PA and PB, we just have one mass moving together that we call the system. So it's PS. Now, if we break that down, we have MA times VA before the collision plus MB times VB before the collision. And that equals, now the masses are stuck together. So the mass part is MA plus MB times the velocity of the system as a whole, because they're stuck together. So this is separate before. Stuck together after. And then the last type is really the same as the one we just talked about, except they're stuck together before and then they separate. It's more like an explosion. So the entire mass of the system is stuck together initially, and afterward, as a chemistry type person, I kind of look at these equations the way I would set up a chemical equation. So the equal sign is kind of where the reaction takes place, if you were to put it into chemistry terms. In this, in physics terms, this is where the collision takes place, or in this case, the explosion. So the masses are stuck together before the collision, and then explosion, I should say. So the mass is all stuck together before the explosion. Then after the explosion takes place, they separate. So if we break that down, once again, MA plus MB stuck together before with some velocity. A lot of times, in this case, the velocity is 0. And then they separate into MA times VA plus MB times VB. Okay, so this is explosion. Stuck together before. And separate after. Okay. We will, I'm going to save example problems for class time just because I think it'll work out better that way. So the last thing we have to talk about here is the conservation of momentum in 2 dimensions. We've talked about objects moving with 2-dimensional motion. In this case, we're talking about when the objects in a system collide and they move off at angles from each other. The momentum is still conserved, but we have to use vector addition to show the conservation of momentum and calculate the momenta of the different objects, momenta being plural for momentum. So the way that works is typically what we're going to have is an object that is sitting still. Object A moves with some momentum. Let's say these are pool balls again. And we know that if a pool ball doesn't hit another pool ball directly straight on, the one that it hits will go off at some angle. So if we have our second one here, which is B, now the momentum of B before the collision would be 0. If it hits it at an angle, or if it hits it in a certain way, this ball is going to move off at an angle. and ball A is also going to move off at an angle some other direction. Now, all of the momentum, don't forget, is a vector quantity. So that would be P prime A. This would be P prime B. PB before the collision was 0 kilogram meters per second. Okay? I'm going to just go ahead and move that out of my way because I'm going to need to put something else there before too long. Okay, so after the collision, these things are moving off at angles. PA has some momentum in this direction and also some momentum in this direction. So we would call this PAX and PAY. Object B also has some momentum in this direction and some momentum in this direction. So this would be PBX and PBY. The thing is, all of the momentum, and again, momentum is a vector quantity, all of the momentum before the collision was equal to the momentum of object A, and that was going in this direction. So after the collision, since momentum has to be conserved, all the momentum that it had before the collision still has to add up to the momentum of object A before the collision and be in that direction. So that means that the PAX plus the PBX after the collision add up to the momentum of object A before the collision. Get rid of those. So PAX and PBX. Oh gosh, that is awfully darn close, isn't it? I'm pretty good. Equal PA before the collision. Okay? So again, we will save example problems for class time. That makes your video quite a bit shorter. And it'll make the example problems probably a little easier to follow, hopefully. So we'll see you in class. Thanks.